gamma 1 to n minus 1 non-zero.
The question about the homogeneity here is in H, and the fact that H doesn't depend.
Yeah, and it's also, I said that everyone's measuring the same thing. That also gives you homogeneity in L and C, and that's critical for closed form. What I say is true in principle. You see the same phenomena in the general case, but if you want to actually work out the eigenvalues by hand, you need homogeneity in there. But it illustrates the principle of what actually happens. Okay, so you've got to have n minus 1 non-zero eigenvalues in your Laplacian. If you don't do that, you are guaranteed to have confusion in your network. So you can only achieve or modify the consensus or disagreement dynamics if and only if you have a spanning tree in the topology. That means there has to be a spacecraft or a person that where if the communication starts there, it eventually reaches everybody. If that's the case, then you can avoid confusion. So this is the problem of, if I have a leader, if I tell you all what to do and everyone tells everyone else, eventually you get this without any confusion. You get some transient dynamics in the confusion, but you can control it. Okay. This one, interestingly, only requires n minus 1 receivers in the system, not n squared. There's only n minus 1 links. And I can give you some examples of this. You only actually have to have one transmitter in the system. If I stood here and just yelled at everyone, then there would be no confusion. I think you would agree. That's pretty much what I'm doing right now. But I think there's still confusion. If I sit here and yell, there should be, theoretically, no confusion. Because you're all hearing. As long as you're all hearing, maybe you do actually need to be listening. So there has to be n minus 1 receivers of the information there. But there only has to be one transmitter. So that's a potential for redundancy. But it tells you what's critical. The receivers are really critical. You have to be listening. If someone doesn't listen, there's confusion that you cannot avoid, even if everyone watches what that one does. So you've got to have n minus 1. Actually, sorry, that means if two people don't listen, then the two people don't listen, you're eventually going to, your network is going to grow with confusion. So actually, I've given you a proof that probably contradicts you something that your mother told you, but here I think we've shown mathematically that it is better to receive than to give. So, and it was Christmas time. Otherwise, you're going to get confusion. But the interesting thing here is that the minimum number of communication links only grows linearly with the size of the network. No, it doesn't have to grow with the square, which is what you get with everyone looking to everyone else. So let me just give you some simple examples of simple communication topologies with spanning trees. And there are two of them here. There's one, this is me, this is you, everyone else, and I'm telling you what's going, my estimate in there. And this is the Laplacian for that. All the talking is in the first column, and all the listening is in the rows, so you're all listening and I'm talking. The eigenvalues there, 1, 1, 1. Here's another case. I talk to someone, they pass it down the chain like this. This is the Laplacian. As you can see, it's quite different. But the eigenvalues are still 1, 1, 1. Now, both of these cases, you can control the eigenvalues of the confusion. They have very different transient responses. As you can imagine, the transient response in this case is worse, because it takes time for the information to get from me all the way down to the last person. Whereas here, one step, everyone knows what I'm thinking at least. So, and actually, interestingly enough, this is a Jordan block form in here, which is where you get the very large transient. That should be motivating a problem for your class. Okay, now let's think of the general case. I used those three examples to illustrate the basic principles, but you can now go on to think about how to design the best algorithm for doing that. And I don't have time to go into much of the details, and it gets pretty messy. But the way you basically do it is you write down the dynamics here, and it's pretty ugly looking, and you write down all the things you get to choose in that dynamics. You can choose a controller gain, the local Kalman filters, that's a single Kalman filter on each spacecraft, the local receivers, the local transmitters. And you can make all of those different variables in there. And when you, don't worry about too much about the notation, but just look at all the colored pieces. Those enter this problem structurally. So you know it, where, sorry, everyone who's talking to everyone else would give kind of a full matrix type of Kalman, because you've got information from every possible source. In this case, you only have information from selected sources, so what this notation is a big simplification for is you can only fill in the pieces of this matrix where you receive a piece of information in there. And now you have a structured design problem. You can now set up your standard algorithms for Kalman filtering or LQG type design, but now the problem is you're not looking for full matrices, you're looking for structured matrices. So here's the full dynamics. This is a huge matrix, not just because it has quite a few terms, but the dimensions are enormous. And now, to set up a nice design problem, you want to weight the transmitter gains, and then find the estimator values. There are two problems in this. One is that the Kalman filter, transmitter, and receivers are structured matrices, and the second one is FH appears bilinearly in there. So, but both of these, either of these effects would actually cause you to lose convexity in your standard design problem. This one isn't such a serious one because it's actually an additional degree of freedom. When you're doing a Kalman filter gain, H is the C matrix that would be specified for you. Now you get to pick it. This we can only convexify, but our experience in doing this has generally been very, very good in doing this for spacecraft problems. But that's the basic idea. I'm not going to tell you the trick. Well, there's the trick. You can read it in the slides, but I don't have time to go over it. So let me just skip here to doing the examples. So,
excuse me, in this case it's not true anymore, it's more the important reliability of the receiver and
so it's not?
It's not true anymore that it's more important the reliability of the receiver and reliability of the
no, it is still true.
It's still true? I don't know how this
it would be the, well, let's say if there are two people who are not listening, then a difference between the noise in those two vehicles will propagate through the system and give confusion. Because there's some noise they can't resolve between the two. So it's still true. The closed form solution is where you can actually see it mathematically. So here I've got 3 spacecraft. I don't have the budget, sorry, for this real spacecraft.
Yeah, quick question. So of the 4 cases that you mentioned,
yeah,
which is the one that you would design by if you wanted to have a system? The one with full communication?
No.
The last one? Well, but then there are some cases there where you could run into problems.
You get to control the communication. So you get to control the disagreement, but you may, you will be accepting a trade-off in performance for that particular choice of control. And the severity of the trade-off depends on how far you are away from complete communication. Because essentially complete communication gives you a deadbeat control in terms of your estimation error, for everybody's estimation error. You can resolve that at the next step. And so the only errors are coming from the innovations in the noise, basically, in the process. So it's more like a standard Kalman filter if everyone talks to everyone else. Now, if you have communication which isn't full, then there's some propagation dynamics to that. So you incur an error due to those propagation dynamics. Now, the question here is whether you can live with that error or not as part of your trade-off. In the spacecraft problem, probably not, because you're after such a precise level of performance there. But then again, the spacecraft are huge. These are 500 kilogram spacecraft, and you're running, typically we run 50 hertz update cycles, so if it decays in 10 cycles, you haven't moved the 500 kilogram spacecraft very far in a fifth of a second. So it may be acceptable. But yeah, you're trading off against performance of what you have in terms of the network. The other critical thing here is that if you tell me the topology, I will tell you the best you can do, or at least set up the problem for the best you can do in terms of the estimator design. If you want to compare two topologies, then you're in a combinatoric problem of looking at what's the best possible topology. Suppose I've got 20 spacecraft, but I only allowed 15 links. Which 15 should I choose? I can tell you how to evaluate each 15 and get the best you can do with a choice of 15 links, but you have a lot of possible links. So you're combinatoric if you're trying to choose the topology itself. But once you fix the topology, then you're in this framework we're dealing with here, which is relatively benign. Yeah.
So if I missed it, so the size of the vector that you're communicating, is that pre-specified, or can you also optimize over it?
You can optimize over it, but again, what you get there is you get a rank constraint on the LMIs. So, and it's exactly the same form of rank constraint that you get if you're trying to do a reduced order control design. So,
so you have to try different cases.
You'd have to try different ones to do it, basically. But if you give me the rank constraint in advance, put it into the LMI and suffer the consequences just like you would in a reduced order control design. The other thing is, when I say I communicate to you in this, I don't have to send my entire state. I just have to send one number to you. And the thing is, you use a Kalman filter, it allows you to reconstruct what I thought was going on the basis of being able to observe my estimate from that one number. So I don't have to tell everything. I may be limited in the number of channels, which would put the rank limit on the number I have to send. So yeah.
In this also you can select maybe one as a leader.
You could.
Which is more expensive than others or more reliable, and then use that as a reference to...
You could, and actually that might make some sense in this particular case when you have one combiner spacecraft. Because if you lose the combiner spacecraft, you've lost it all. Yeah. And you could set up the problem of optimal decentralization of the rest of the spacecraft with one leader in there. You could certainly do that. But another interesting point I haven't brought out here is that, in decentralized control problems like this one, a fully decentralized problem outperforms the centralized control design. Now this seems a little counterintuitive. You'd think having one spacecraft knowing everything and telling everyone what to do would be better. But it's not, for the following two reasons. When a spacecraft makes a measurement, in a centralized scheme, in a practical centralized scheme, it has to send that measurement to the main spacecraft. There's noise on the communication, which adds to the noise on the estimate. That spacecraft then updates the estimator, calculates the control, and then sends the control back to the spacecraft. That's a round-trip communication of two cycles, and noise got added in both of those. So if you're in a high-performance environment, what will happen is that round-trip delay, plus the additional noise, means you have to design the centralized one to suboptimally so it's not a problem. So in practice, what's going on with the decentralized one is the information that comes locally can be used immediately for some kind of a control action. And you can get better performance from a decentralized control design, which is certainly counterintuitive when you see centralized being the optimal in the papers. But what I'm talking about is a practical centralized where you actually have to send the information backwards and forwards. So my final demonstration here. We don't have spacecraft at UCSB. We have 3 of these Quasar carts, which is, given the state of the UC budget, this is probably what we've got here. So here we have 3 carts running on these parallel tracks, and the idea is we want to keep a formation of them. Here's the example of the 3 carts. They have to space them